All right, welcome to Engineering Ethics. This is the March 22nd online hangout. This is week 9 of Engineering Ethics. This week we'll be talking about climate change. There's lots of stuff to talk about with climate change. Before I begin, let me just do a couple of housekeeping things. So, like I said, we're on week 9. Last week was spring break, and assignments weren't due last week. One of the things that means, just to start off, is that the lesson 8 discussion replies are due this Friday. So if you didn't write your 3 replies for the Deepwater Horizon discussion, you can still turn those in for full credit until the end of this week, Friday at midnight. I know Friday is Good Friday, and there won't be any class on Friday. I won't be holding lecture on Friday either. But the assignment is still due on that day, just to keep the schedule regular. If you don't want to work on Friday, then you should complete the assignment before then. But lesson 9 this week and then lesson 8 last week. The replies for last week are due this Friday. So make sure you get that done. One other thing to mention is I've caught up on grading. I've graded, I'm pretty sure I've graded all the discussion posts, and I've also updated all the attendance credit. The only thing I haven't graded yet is quiz 7, which was one of those quizzes that required manual grading. So I'm a little bit behind on that. The grading scheme will be the same as the previous quiz that required manual grading. So if you did well on the previous quiz, then you should do fine in this one. Apart from quiz 7, which I haven't finished, hopefully I'll finish it this week. The rest of the grading should be done, including all the attendance grading. So check your grades, see if you have any questions. If you do, ask. Send me an email. I'll probably send around instructions for how to calculate your final grades in class right now. The short answer is you just add up all the points that you have across all the assignments and the attendance points, and then divide it by the total possible points. Every week there's 80 points possible, I believe. And there are a couple of exceptions to that. But if you add up all the points and then divide it by the total possible points, then you'll figure out where your grade is right now. One reason to try to calculate your grades, and I'll like I said, I'll send around instructions for how to do it precisely. But one reason to calculate grades now is that the last day to drop classes is on March 28th, which is next Monday. So if you're doing poorly in class, if you don't think you can catch up to get the grade that you want in class, then you might think about dropping the class without penalty before Monday. I caught up on attendance really quickly about attendance credit. If you signed in for the online credit for the Hangout, you might not have gotten credit if either you submitted the attendance after midnight. So the credit only counts for people who submit the sign-in sheet before midnight. So if you submitted after midnight, I just didn't give you grades, or I didn't give you credit. Also, I didn't give you credit if you got the wrong word of the day. So occasionally students are confused because I have a little bar underneath my name. Let me see if I can get it. Oops. No. There it is. So I don't know if that worked. I don't know if that worked. Okay. I guess my overlay is not working. Well, people have been confused about the overlay and sometimes have submitted the wrong word of the day. So if you didn't receive credit for one of the online Hangouts, it might be because you either submitted your attendance late or you didn't use the right word of the day. If you have questions about that, though, send me an email and I can check my records to explain to you exactly what's going on. If there's any other discrepancies in your grades, send me an email. Let me know. I think that's all the housekeeping for today. If anyone has any questions, just let me know. Either about class or about the assignment schedule, or about anything else related to class. right, well, if there's no questions, I'm going to go ahead and get started, jumping into lecture. All right, so we're on lesson 9 this week. This week is, we're going to be talking about climate change. Climate change is a big deal. It's a really big issue. It's probably the most important issue facing humanity today. A lot of geopolitical issues, a lot of other problems that humanity faces partly are the result of climate change. I mean, just for instance, just to get us going, where's my... the war in Syria right now, hundreds of thousands of people are dying right now in Syria. A lot of this is because of displaced farmers who are suffering from drought in the region. Heavy drought that's been going on for years. This drought has displaced lots of people. You know, the crops aren't growing, and so they're having to move to try to find water. And this big displacement of people partly sets the grounds for the political unrest that leads to the wars that we see today. Right, so this is an example of how climate change is already resulting in human death and tragedy. So we're going to be talking about climate change. This week, there's no particular issue that I want you to look at. I want you to look at the phenomena of climate change generally, and in particular, the human contribution to this, the relationship between global climate phenomena and human industrial activity. Right? We've looked the last couple of weeks at some major engineering disasters, major environmental disasters. Last week we looked at the Deepwater Horizon, which is one of the largest environmental disasters in history. And it shows you the tight relationship between the state of the environment on the one hand and human industrial activity on the other. So I think the very fact of climate change is a problem for engineering ethics, and there's lots of room to talk about different kinds of things related to engineering ethics. So what role industry has in this process, what role government and government regulation has in this process, what kinds of engineering solutions might we come across to help mitigate the effects of climate change. There's lots of things to talk about with relationship to human technological and engineering practices and the effect that we have on our environment. So I want to talk about some of these things. My big idea for this week is to give you the opportunity to do some research yourself if you haven't spent time going into the science on climate change and going into the implications of climate change. Then please use this week to do some research and teach yourself something about this really important event. There's no specific thing I want you to read, but just in terms of housekeeping, remember this is week 9. Next week is your research project. So next week for next week's lesson, you will be asked to submit a case study of a case of your own choosing. The post itself should be normal length, 350 words or more, but the content has to be a case analysis, and you have to choose your own case, and you also have to do some scholarly research to back up your analysis of the case. I have all the instructions on the lesson 10 assignment. The instructions are pretty detailed, so you probably want to start early if you haven't already started already. And I'll just let you know right now that the credit for lessons 10 and 11 is worth more than a normal week's post. A normal week's post is worth 30 points. The research project is worth 80 points for lesson 10 and 11 separately, so it's 160 points total. So it's a big chunk of your grade. It's really important that you do a good work on this lesson. Good. So this week is sort of the run-up to your own research. I have some resources here that I want you to look at. My plan for this lecture is the first thing I want to do is talk to you about the history of temperature in the open thread for discussion 9. I have my little cartoon, but then after that I have a couple of graphs about the history of climate on the planet, and I want to go over some of the details of these graphs just so you have a sense of the history of climate change, and so that you can put into perspective some of the things that we're seeing today. After I talk about the history of climate change, I want to talk about some of the facts that we're seeing today, what climate change actually looks like on the ground today, and what the different countries are doing about it, what they're pledging to do about it over the next few years, and what that means for our immediate future for the rest of the century. After we do that, I want to talk about my buddy John Lawhead. He's a postdoc at USC, and he's doing research right now into geoengineering. Geoengineering is where we engineer large-scale projects to help mitigate or deal with the effects of climate change. Geoengineering projects are controversial, and there's lots of ethical issues involved. So I want to talk about some of his research and about what we know about geoengineering as a response to climate change. This is sort of new stuff, and some of it's very scary, so it'll be fun to read. So that's the plan today. Let me see if there's any questions before I go on. Kevin mentioned like China and their air pollution. Yeah, China is a big contributor to air pollution. In terms of raw quantities of greenhouse gases, China releases the most greenhouse gases of any other country. But they also have a huge population. If we were to do it per capita, then the US releases more greenhouse gases per capita per individual. There's just a lot fewer of us. There's a little over a quarter million citizens in the United States, and there's a billion and a quarter in China. So China has a really big problem with air pollution. They're starting to sell bottled air in China, bottled in Canada, that kind of stuff. I guess one thing to mention here, though, is that the US is not very great on climate change either, greenhouse gases. I think I mentioned this before we went to break, but there was this huge methane leak in California last year. This was, in fact, we were looking at the Deepwater Horizon spill. You remember the Deepwater Horizon spill, when it started happening, no one really knew what to do, and there was about a week, about 10 days, where they were sort of scrambling around for responses because they really didn't know what to do. Well, the same thing, history repeated itself almost exactly in this methane leak. The methane leak wasn't a mile underwater. It was in the foothills around Southern California. But this was a huge methane leak, something like 97,000 metric tons of methane, which is effectively double what the entire LA basin releases in methane every year. So just this one leak, twice as much methane as all of Southern California, all of the LA region releases over the year. It's a huge spill, and it was the same kind of thing where when it started, we didn't really know what to do. We didn't know how to stop it, and so it just kept leaking for months. It's closed now, but this is while we had this class, this is one of the worst environmental disasters in history happening during our semester. So California isn't any better on these issues. The United States isn't any better on these issues, really. And the responsibility, I can link to this Science article. This is some research about the extent of the damage. And one thing that's clear is that the reason for this isn't because of volatile environmental calamities. It's largely for the same reason that the Deepwater Horizon spill happened, which is failure to keep up with standards, failure to keep up with regulatory standards, and completely gutted regulations in the first place. So the regulatory standards themselves were very, very low, and in some cases just not being enforced. And then even on top of that, the facilities were not operating to standard already. So again, we have major violations of regulations, major violations of ethical codes, resulting in huge environmental disasters. In the discussion forum, some people are already talking about the VW emission scandal in relation to this climate change, where we see this very clear trend of large corporations doing huge environmental having a huge environmental cost, hugely environmentally destructive, and doing everything it can to avoid punishment, not even just avoiding punishment, but even avoiding recognition that they're doing it at all, right? So they're lying and cheating in order to make money, in order to steal as much money as they can before things go to shit. And we'll see how bad things will go to shit in just a few minutes. Yeah, in Newark, there's smoke blowing from factories. But Kevin's right. So someone mentioned the factories that we see in Newark blowing smoke into the air. But then Kevin mentions that but there's limits on how much smoke those factories can produce, and that's exactly correct. They can't just release smoke or release gases in the air without regulation. There's all sorts of rules about how much they can release, what kind of contaminants they can release, and so on. And then different states have different regulations, and then there's federal regulations on top of this. Sometimes these are more strict than others. The goal here isn't to stop all pollutants. The problem is that we're polluting so much that it's destroying the environment. So let's get a good picture before we. Oh, one more thing before we get going. And this happened just over the break also, which is that we crossed the 2 degrees centigrade threshold. So for years, for decades, in fact, scientists have been talking about 2 degrees Celsius as being a cutoff point, a major threshold. If we cross that threshold, the environment will start displaying dynamics that we can't anticipate, that are unlike the dynamics that we're used to. So the 2 degree threshold is supposed to be a point of no return. And for decades, scientists have been warning us that if we ever cross this threshold, then then we're going to face really serious climate disaster. And so they've been trying to get us to instantiate climate change since the 70s to help prevent us from getting to that 2 degrees Celsius mark. Well, we just crossed that 2 degrees Celsius mark over the break, especially in the northern hemisphere where a lot of these greenhouse gases accumulate. There's a temperature anomaly. We're hotter than we've been. In fact, we're 2 degrees centigrade hotter than we've been. So this brings up a point, and maybe this image can help us start. So I've seen some questions, some skeptical questions on the discussion forums. Some students saying things like, I can tell that it's been hot this winter. We didn't have a winter. We had a week of snow. It's been a little bit cold this week, but we really haven't had any cold temperatures. And in fact, this has been the warmest winter in recent memory, and 2015 was the hottest year on record. I didn't have this on the lecture because I wrote the lecture. Actually, I wrote the lecture in 2014, so I updated it for 2014 when 2014 was the hottest year on record. But that record's been blown away. 2015 was easily the hottest year on record already. So you can tell that maybe it's getting warmer, but some people are confused, and I saw some criticisms wondering that it's not always warmer. We also have these record low temperatures. Some of the cold days that we've been getting have been record lows also. And so how does that fit with the idea that there's global warming if we're also seeing very cold days? And it's a good question, right? Because we do see some warming and some cooling. Here's a trend. You see it's not warming everywhere. In some places it's actually cooler than it was, but in some places it's much, much warmer. And this brings us to a very, very important point. It's that the issue isn't just global warming. The issue is climate change, and the emphasis here is on change. What has been happening is not just a steady increasing of temperature everywhere, but instead a disruption of the normal patterns of climate and temperature. It's this disruption that matters most. So we've been talking in class, hopefully I prepared you for this, we've been talking about integrity as an important feature of ethics, but also just an important feature of organization generally. In order for an organization to stay organized, it needs to have some integrity, it needs to have some stability in the face of perturbation. And so what's really important about climate change is that a lot of the stability that we've seen has gone. So we're seeing not just increasing temperatures, but we're seeing temperature anomalies all over the place. So if you remember from 2 years ago, the 2014-2015 winter season, we had an abnormally cold winter that year. The 2014 was, at the time, the hottest year on record, but for the Northeast especially, we had these temperature anomalies. I don't know if you remember people talking about the polar vortex, where cold temperatures from the Arctic came down and they dipped unusually low to cause a bunch of blizzards in the Atlantic Northeast. So this is an example of a temperature anomaly, a cold anomaly. In fact, this was one of the only cold anomalies on the entire planet. The Northeast, our little region, was one of the only places on the planet in 2014-2015 to experience relative cooling like this. Almost everywhere else on the planet was abnormally warm. But the point here is, again, the point here is not just that everything gradually increases in temperature, but but temperature is disrupted, and so you have patterns of climate that you don't see before, patterns of climate that are displaced from normal. It's this displacement from normal, it's this lack of stability that characterizes climate change, and it's a really important feature we want to talk about. Yeah. So let me just, I'm going to hand draw a little graph. Okay, this is a very crude little graph, but here's time and temperature. When we think about global warming, what we mean is really shifting the whole temperature scale, right? So the whole bell curve. You guys are engineers, so hopefully bell curves and statistics, right? So this first curve, imagine this is a bell curve describing normal weather patterns. Some days are really cold, some days are really hot. Oh no, I did this wrong. This should be temperature. Okay. Time. Sorry, this is a crude drawing. Temperature, so low temperatures, high temperatures, and how often we experience those temperatures. So on the original curve, you have low temperatures sometimes, right, very low temperatures sometimes, very, very high temperatures sometimes, not very often, and most of the time you're somewhere in the middle. And what you see with global warming is that this whole curve shifts a few degrees to the left, right? Which means everything gets a little bit hotter, but that doesn't mean that you see everything hotter all the time, right? So most of the things fall in this middle zone, the average temperatures, and those don't change very much, right? So most of this overlaps with the old graph. So most temperatures that you see on a daily basis look like they did before. But what you see are more extreme high temperature events and fewer extreme low temperature events, right? So the whole curve shifts. And because we get more extreme high temperature events and fewer extreme low temperature events, you get this disruption to the normal pattern of climate, so that all sorts of strange things start happening, things that we wouldn't expect. For instance, I don't know if I still have this. Oh, I had an image up of hurricanes. We're starting to see lots and lots of hurricanes, more than average around the equator. Already we're starting to see hurricanes even well before hurricane season. And these hurricanes are a lot more powerful than normal, right? When the temperature, so hurricanes are energy, spare energy in the environment, whipping up a storm. And the hotter the temperature is, the more energy there is to dump into these hurricanes, the more hurricanes you see, right? So the hurricanes are these climate phenomena that are going to be, disruptive, chaotic climate events, causing lots of disruption, and it's going to be happening more often than we would expect, right? It's this disruption from what's normal. It's moving away from these stable climate events. Okay. Okay, let's talk about the history of climate change. I'm sorry, let's talk about the history of temperature, sorry. And we'll come back to how complex the system is. Okay. So this is I'll basically be retelling a lot of what I say in the open thread, where I link to some of these images. And these images all come from a friend of mine, John Baez, who's a mathematician at the University of California, Riverside. He works on mathematical physics, but he's also really interested in temperature. Really interested in climate change. And he has this really extensive and well-sourced document on the history of temperature, going back to the start of the planet. So, and this is where a lot of these graphs come from, which he sources and gives in a lot more detail. So my goal is to talk to you about the history of temperature, how temperatures have changed since the beginning of the planet. The Earth was formed about 4.6 billion years ago. You can see on this graph, 4.6 billion years ago. And at the time, it was just a big ball of molten rock. It's very, very hot. So this, we're going from the past to the future as we go up. And then on this side, it's warm, and on this side, it's cold. You see that the graph here isn't very detailed because we don't have a lot of records of these events. We have some records of these events to get the general shape, but it's not really until we get into the recent history that we have enough data to fill this in with any detail. And we'll look at more specific graphs over here. But just to get a very general picture of the history of climate change, right? It starts off very, very hot. The Earth's a molten ball of rock, and then it cools down. And in fact, it cools down very cold. And we know that at some point before life began, so life begins right here, the Cambrian explosion is where life proliferates. There's some early kinds of life back here, but life doesn't really get going until the Cambrian explosion about 570 million years ago. Before that, we know that it started off really hot, and it got cool, and then it warmed up and got cool again. These things, we're not exactly sure why this happens. We know it has to do with the ice cover on the planet. So ice on the planet, ice is white, and white reflects light. And so the more ice that's on the planet, the more light gets reflected and the less heat gets absorbed by the planet. And so we know that in a really, really cold planet that's covered with ice, it should stay cold. And so there's these interesting events where it gets really cold and then bounces back to hot and then comes back cold and then bounces back to hot. And importantly, as we look at this graph going on, you don't have to recognize all the details, but what you should recognize is that this is not a steady pattern. This is not like a clockwork pattern where sometimes it's cold and it switches hot and cold in a regular way. Right? In fact, this is the first and most important lesson about climate change, is that the climate is a chaotic system. It's a complex and chaotic system, and its patterns, its sorry. Where am I? Here we go. The climate is a complex system, and the patterns of change in the climate are multifaceted. There's lots of variables going into how this changes. I already talked about one, the ice cover. How much ice is on the planet has one impact on how hot or cold it is. The more ice it is, the cooler the planet stays. It's harder for the planet to warm up when there's more ice cover. This is one of the reasons why it's so important that the polar ice caps are melting, because it means that there's less ice cover, which means that we absorb more heat, which makes the global warming process go that much faster. Okay, so this general pattern, warm to cold, Cambrian explosions when life starts, and all of our oil, by the way, comes from creatures who lived in this period, especially the Carboniferous period. So one thing to know just about life on the planet is that early forms of life figured out how to live for themselves, but they often used techniques that were completely destructive to the environment. And several times over this early period of climate, there are these mass extinction events where huge percentage of the life on Earth dies. Sometimes up to 90% of the life on Earth dies. And almost every time it's because an organism starts doing things that's really bad for every other organism. So one example of this is woody, pulpy structures in plants. So most of the oil that we have are the remnants of plants, dead plants and animals, but mostly plants. And the reason that all these plants stuck around for such a long time is because for a very long time, no other organism knew how to digest the plant material. Right, so woody, pulpy, fibrous, organic material is very hard to break down and digest. The cell walls and so on are just very thick. And in the early part of the planet, there were no creatures around. There's no bacteria or anything that was able to break the stuff down. And so when creatures with woody, pulpy bodies died, their bodies just laid around, not even decaying. Right, decay happens because other organisms break it down. So these plants would die, and they would just sit there and pile on top of each other. And so you get millions and millions of years of dead animals piling on top of each other until you get thick cakes of this organic material. You cover that over with pressure and temperature for millions of years, and you get oil. But in the meantime, before those million years are up, you have all this decaying matter around, and it causes non-decaying matter around, all this material that's not breaking down. Similar to like our plastic, right? We have a bunch of plastic that nothing that exists today is going to break it down, and it's polluting lots of places in the environment. It's polluting the oceans and so on. This is an example where we're producing this stuff that nature doesn't have existing mechanisms for processing. But human beings aren't the only creatures to do this. This is actually a very common event in the history of the planet, and it leads to extinction events more often than not. The biggest of the one of the biggest of these was the creatures that discovered how to process oxygen. I'm sorry, the creatures discovered how to process carbon dioxide and turn it into oxygen. So oxygen doesn't exist normally, naturally on the planet. All the oxygen in the atmosphere is produced by other organisms. Right, so all the oxygen that we breathe is produced by other organisms, like the plants that breathe out oxygen. But again, it took a long time for organisms to figure out how to use this oxygen. So the first organisms that figured out how to burn carbon dioxide and turn it into oxygen, they were basically polluters. They were releasing tons of oxygen. Oxygen was a poison, and that oxygen killed off most of the other life on the planet until some organism figured out how to process the oxygen and was able to restart the living processes. We're ancestors of those organisms, those smart organisms who learned how to process oxygen. Okay, so let me go back to the graph. Okay, so early period of life, lots of temperature fluctuation, back and down, very complex system, right? This is not like clockwork. There's lots of variables affecting whether temperature goes up and down over this period. The Permian division here separates sort of early life from the period of the dinosaurs. This is the period of the dinosaurs, Triassic, Jurassic, Cretaceous. During the period of the dinosaurs, the average global temperature was very warm. In fact, much warmer than it is now. You see we're in a relatively cool period. And in fact, now we're at the low end of a trend towards cooling. We've been, as a planet, cooling since the age of the dinosaurs, where it's been much, much hotter. The temperature being much hotter is partly what allowed the dinosaurs to survive. Big lizards can't exist anymore today. There's a size limit on how big lizards can grow, and that partly has to do with the temperature of the atmosphere. So I've already talked a little bit about this, but we're starting to see that the temperature and the climate has deep interconnections, deep interdependencies with the living systems on the planet. Right, and what kind of life can exist changes the temperature and the climate changes what kind of life can exist. These are symbiotic systems. These are mutually reinforcing, interdependent systems. The composition of our climate, let me just say this one more time, the composition of our atmosphere is the product of organisms that live on the planet. Right, this isn't just atmosphere that would be here whether or not anything was here. The atmosphere on this planet is created and built by the organisms that live on this planet. Right, the oxygen and so on is generated by the living systems. So the nature of our climate, the nature of our atmosphere is directly dependent on the living creatures in it. So when it was really hot, you can get these really big lizards walking around. You also get really big insects and so on. You can get insects that are several feet long. And that has to do with the composition of the atmosphere, how much oxygen is in the atmosphere, and also the temperature of the atmosphere. Nowadays, there's not enough oxygen in the atmosphere to let insects breathe. Insects don't have lungs, and they don't breathe through their mouth or anything. Most insects breathe through little holes with diffusion. There's little holes on their side, and gas can diffuse in and out of those holes. So most insects don't breathe, but that only works if you're in a very oxygen-rich environment. If it's an oxygen-poor environment, then you can't get enough through diffusion for that breathing method to work. So when it was oxygen-rich and very warm back in the period of the dinosaurs, you get big bugs and so on. But now that it's cold, you don't see those kind of creatures. As temperatures start cooling down, what you get is the rise of the mammals. And so from 65 million years ago, 65 million years ago is the KT event. This is when a big asteroid hits the Gulf of Mexico and kills off all the dinosaurs, except the birds. And then after the dinosaurs are extinct, you have the age of the mammals. So this last little bit where we see this general cooling trend is the age of the mammals. This is where all the mammals evolved. There were no mammals before then. And we're the direct ancestors of those animals, of those mammals. Right, so our ancestors evolved in this period of time. Okay, so let me check if there's any questions or comments. Oops, let me not do that. Fuck. Okay. Let me check if there's any questions or comments. Anyone have any questions or comments on climate change? right. Okay. So let me keep going on. So this is the big picture from the beginning of the planet, picture of climate again. And the point here is to see the climate changes quite dramatically over the course of the history of the planet, and it changes in ways that have direct bearing on the organisms that can live in those climates. And it's a chaotic system. It's a complex system. If you want to know more about chaos theory, come to lecture tonight, and I'm going to talk about chaos theory a little bit. But you can see that we're on this cooling trend. And that trend is more clearly established here. So this graph is just looking at the last 65 million years, right? So we're just looking at this last little top bit of the climate. 65 million years, again, is the history of mammals. This particular graph is taken from ice cores in Greenland. The ice sheet in Greenland has been there for millions and millions of years, and you can dig down these. Oh no, I'm sorry. This isn't Greenland. This is Vostok. Vostok is in Russia. So the ice sheet in Russia has been there for millions of years also, and you can dig down these pipes that will take a core sample all the way down, and so the collections that you get from the bottom will, and they can do this, a mile down, even more than a mile down, and the stuff you get from the bottom will have been laid down millions of years ago, and so the atmospheric composition trapped in those ice crystals will reflect the temperature at those times, and so you can recreate a model of temperature going back fairly long from these ice cores. Again, you can see that as we get closer to the present, our data is a lot better. Over here, our data is a lot sparser. We have to make a few more guesses, but over here, our data is a lot more solid. And we're going to zoom in just on our recent temperature in just a second. But I want to point out a couple of really awesome things about this graph. Again, first of all, it's a complex system. This is not going up and down like clockwork. This is not a regular pattern that we see. In fact, it's hard to see any patterns at all. There's this peak, and then it's generally cooling, and you can see the trend is towards general cooling. But there's all sorts of weird things happening here. So for instance, there's this really dramatic cooling event around 35 million years ago, where the temperature seems to plateau for almost 10 million years. It's very interesting. And then it rises again. What causes this kind of thing? There's lots of different things that can cause these kinds of changes in climate. I guess I should start by saying that these kinds of changes in climate are not caused by human beings. In fact, human beings aren't around at all during this time. The earliest Homo sapiens come onto the scene about 2 million years ago. I'm sorry, the earliest hominids come onto the scene about 2 million years ago, and the earliest Homo sapiens are about 200,000 years ago. Modern humans are about 80,000 years old, so we're just at the very tail sliver of this. And human industrial activity is only about 200 years old. So none of human activity is demonstrated in these graphs, right? This is all the fluctuating climate before we even got here. And it does these really weird things. What might cause these kinds of changes? Well, there's lots of things that impact climate change in these ways. One thing we've already talked about is ice cover, right? How much ice is on the planet changes, has an impact on how these temperatures fluctuate. The more ice on the planet, the colder things get. The less ice on the planet, the warmer things get. And I mean, you might think that it's interesting at all that there's ice on the planet at all, because we know that it's been much, much warmer. We don't really know how much ice was being preserved when things got really, really warm. But we've made ice packs, so somehow we get into this cooling cycle despite having been really hot. Why are we in this cooling cycle? These are very good questions. Part of the change has to do with the change in the composition of creatures on the planet. The animals on the planet, and the plants and the animals, and the bacteria especially, have a big impact on the climate. And so as those compositions change, so too does the climate. There's other things that change the climate. One thing that's often brought up here are called Milankovitch cycles. So the planet does not go in an even orbit around the sun, right? So if we were doing an even circle orbit, it would look like that. But in fact, our orbit is eccentric, and not only is it eccentric, but we also wobble on our axis by a couple of degrees. Right? So these wobbling on our axis as we go around the sun has an impact on how the light hits the sun, how the light from the sun hits the planet. And the angle of light on the planet has an impact on how much warming the planet receives. So you get these fluctuations because of the change of the Earth around its pole and the changing eccentricity of the orbit of the planet. You get these variations, and this kind of graph shows you these kinds of variations where, let me see. Oh no. Oh no, this is the graph I want. Yeah, so this shows you the changes in temperature that are forced through changes in the Milankovitch cycles in our orbit. So precession, obliquity, eccentricity, these all have to do with changes in our orbit and changes in the orientation of the axis. And this is the effect it has on temperature. And you can see where these line up a little bit, so that some of the changes in temperature can in fact be accounted for by changes in the Milankovitch cycle. So this is starting to hopefully give you some sense of how complex this thing is, right? So we have to take into account the position of the sun, the planet relative to the sun, the composition of life on the planet, the ice cover on the planet. The composition of life also impacts the composition of the atmosphere, and that's going to have an effect on climate also. If we release more greenhouse gases in the atmosphere, then that's going to make things warm up and so on. Right? So all these things are going into the mix, and that's why we see the climate being as chaotic as it is. Right? Again, the climate is one of the most chaotic systems we've ever studied in science, and the kinds of models that we have to develop in order to test this are some of the most complex and computationally intensive models that we've ever developed. And we know with some certainty that the Milankovitch cycles can explain some of these variations, but we'll see shortly that the variations in temperature that we're seeing now can't be explained by the Milankovitch cycles. So one more thing about these strange patterns, right? So we have this period of relative stability, and then it warms up, and it seems relatively stable again here. It's sort of not continuing this trend of global cooling, but then we get here, and then this cooling starts until we get to where we are now. Notice that not only does there's this trend of cooling, but there also seems to be a trend of greater variation, where the difference between the peak highs and the peak lows are greater than they were back here. That might just be an artifact of more data, but it seems like the fluctuation in temperature is also increasing over here. One last thing I want to mention about this graph, it's really, really interesting, is this right here, the PETM. This is the Paleocene-Eocene thermal maximum. Paleocene-Eocene thermal maximum. So this is a period of climate change in the planet's history that represents one of the most dramatic one of the most dramatic sharp increases and sharp decreases of temperature over especially the period of the mammals, but that we know about. Right? So this is a climate extreme event where it goes from a low temperature to a huge peak and then right back down almost immediately. And you really don't see that kind of anomaly anywhere else. Sometimes you have these big drop-offs or these big come-ups, but this kind of sharp little peak is a little bit anomalous. And it turns out that this peak represents a temperature change of about 2 degrees Celsius, about the kind of temperature change that we're seeing now, where humanity over the last 150 years has changed the temperature on the planet about 2 degrees Celsius. So that's about the same extent as this spike. We have no idea what caused this spike to happen. We have no idea what instigated the PETM. And more importantly, we don't know what caused it to stop. We don't know what caused the rapid decrease in temperature in this period. But here's what we do know, that this going from the low to the peak to the low again happens over about 170,000 years. Right? So remember, this is a scale of 10 million years each tick. So that little bump there is about 170,000 years. We're seeing a similar climate change, about 2 degrees Celsius, happen in the course of about 150 years, right? So that's several orders of magnitude faster than this happened in nature. This drives home the point that the kind of climate change that we're seeing now is completely unprecedented in the history of this planet. We've had climate extreme events, and the temperature has been much hotter than it is now. But we've never seen the kind of rapid change that we're seeing today. As far as the climate record, we don't see these massively extreme events. We do see dramatic changes in climate, but they happen over long time periods, right? This PETM takes place over 170,000 years. Climate change today, the same magnitude, but taking place in 150 years. That's very scary. But this is the scariest image that I have. So this is poking down to just the last 20,000 years. Actually, let me go to the let me go just really quickly one before this. Yeah. So this graph shows temperature change over the last 1.35 million years. So the scale isn't consistent. This right here is blown up. But the rest of it is for the last 1.3 million years. Again, like I said, 1.3 million years is about the time scale of hominids. That means our earliest hominid ancestors, earliest human-like ancestors, show up on the scene about 1.3 million years ago. Homo sapiens evolved about 200,000 years ago. So our evolutionary story starts about right here. And we become what's called behaviorally modern human. Yeah, behavioral modernity. So Homo sapiens have been around for about 200,000 years, but behavioral modernity, where modernity means that we're living in groups, we have language, we have art, we can make fire, we have some rudimentary tools, and so on. We're not agricultural. Agricultural happens much later, but we start the process of becoming recognizably modern humans, right, where we have language and culture, tools, art. We start that about 80,000 years ago. So Homo sapiens come onto the scene about 200,000 years ago, and we become behaviorally modern humans around 80,000 years ago. So one thing that points out is about half of our existence as a species was not lived as behaviorally modern humans, where we didn't have language, we didn't have tools, we were basically living in the jungle like the other animals. It's only recently that we started doing things that look like modern humans about 80,000 years ago. And notice over this time period, temperature has gone up and down. We've had cold periods, we've had hot periods, cold periods and hot periods. 80,000 years ago, behavioral modernity. But only 20,000 years ago, only about 12,000 years ago, sorry, let me say that again. About 12,000 years ago do we start agriculture. And so that's what this last graph shows. So this is the last 20,000 years of human, there's 20,000 years before the present, which means that human beings are behaviorally modern. And about 12,000 years, about right in here, we start agriculture. So this dip in temperature is the last ice age that human beings went through. It's called the Younger Dryas. It's not really the biggest cold spell. This is the Younger Dryas right here. We've had other cold dips like this. In fact, our recent history has had these very cold periods followed by very warm periods. This is partly why human beings had to migrate around the planet, is because the temperature kept changing so much. This is why we left Africa and took over the rest of the planet. For most of human history, we were migratory hunter-gatherers moving around as the climate and weather dictated to try to find fertile foraging grounds. About 15,000 years ago, we have a temperature spike, and then we get this period of rapid cooling until we get to the Younger Dryas, which was the last big cooling period, the last big ice age that human beings lived through. And in fact, in some sense, we remember these things. Saber-toothed tigers were still around back here, woolly mammoths and so on. We hunted them back during this period. But after this, temperatures warm up, and this is where we start agriculture. So human agriculture, in other words, where human beings stop moving around and settle down in a single location, where we plant crops, we domesticate animals, and we just tend to the land as opposed to moving to try to find better land. All of that happens within the last 12,000 years. And you can see on this graph that that agricultural change in human behavior corresponds with an unusual stability in the climate. For the last about 12,000 years, the climate has been unseasonably warm and unseasonably stable, unprecedentedly stable. The temperature over the last 12,000 years hasn't really fluctuated by very much at all, compared to the kinds of fluctuations that humanity has seen over its history. This is the reason why we were able to become an agricultural species, is because the climate had stabilized to the point that it supported our sedentary agricultural lifestyle. If the temperatures were fluctuating rapidly, then we couldn't have settled down, we couldn't have raised our crops, right? So agriculture and all of civilization that comes from it, right? Reading and writing, all the technology that you know of, industrialization and so on, all of that happens because the climate stabilized about 12,000 years ago. We're an agricultural species due to the climate. Over the last 10,000 years, we've had some cold periods, some warmer periods. Some of this stuff is in written record. We're a little ice age. People talked about that back in the 1800s, 1700s, 1800s. It was very, very cold in winter in Europe. But notice that that amount of cold is quite dramatically different from this amount of cold during the last ice age, right? So the kinds of fluctuation in temperature that we've seen over the last 10,000 years actually represents incredible stability. And this is important because this stable period is over. No longer is temperature within this stable zone. We've put enough greenhouse gases into the environment that we've knocked ourselves out of the stable zone, and so temperature's rising rapidly. That means, first of all, that the conditions that allowed us to be an agricultural species have vanished. This means that crops are going to fail. This is why we're seeing these wars and so on in Syria, because crops are failing. Drought is having a huge impact. Temperatures changing what crops you can grow, what time periods you can grow them in, and all of our patterns of these kinds of agricultural behaviors have changed. Right? It used to be very stable, where you could basically count on your crops coming, bearing fruit the next season. But this is going to change. This is changing very rapidly. Right? We've knocked ourselves out of the stable point so that we have these huge climate problems. So let me say this one more time. The reason that we have the agricultural technologies that we do is due to stability in the climate. When this stable climate is over, that means we're going to have to change our lifestyles as radically as the change from pre-agricultural to agricultural technologies were, or the change from agricultural to industrial technologies were. All of these changes have been incredibly pervasive and have had huge impacts, not just on humanity and our own cultures, but on the globe itself, the climate across the globe. And now that we're out of this stable pattern, in some sense, we don't really know what's going to happen. I mean, we know what the effects are going to be. Sea levels are going to rise, crops are going to fail, and so on. Geopolitical instability all across the planet. But we don't know whether warming will increase, whether something will make it come back down into a new ice age. These kinds of things are very difficult to predict because the climate is such a complex system. The only thing that we know for sure, and really the only thing that we need to know, is that this period of stability is over, that the stability that we've enjoyed for our history as an agricultural species has come to an end. Let me stop here and see if there's any questions or comments, thoughts from anyone in class. Hopefully this discussion of the history of temperature, people find it helpful for understanding what it means when we say 2 degrees Celsius temperature change now, right? Scientists are all really surprised that there's a 2 degrees change in temperature. But how much, what does that really mean? How common is it in the history of the planet? Well, as we've seen, changes of 2 degrees of temperature has happened plenty of times over the history of the planet, but it always is associated with also rampant changes in the biological composition of the planet and the atmospheric composition of the planet. Right, and these have impacts on what on everything else. Questions? There was a discussion forum post in the lesson 9, someone who was skeptical of climate change, talking about how sometimes things cool down, sometimes things heat up. How can we really trust the science if if the scientists are saying that it's global warming, but then we see these? I hadn't given the word of the day, no. How can we be certain of the science if things are changing so fast? Doesn't temperature change on the planet anyway? Isn't this just a natural process? Well, hopefully this discussion gives you some indication of what a natural process means, and in fact that what's natural is not what we've been seeing over the history of our species. That in fact what we've experienced over the history of our species for the last 12,000 years. And remember this: every culture that you know of, every story, every myth, every religious practice, every artifact that you know of comes from this period of time. Right? This is all of human history as far as we have record of. Right? This is recorded human history, and that period was really the anomaly. If you look at the temperature over longer periods of time, you really don't see that kind of stability anywhere else. Right? We were lucky over the last 10,000 years to have this kind of stable climate. So it's really important that the climate has destabilized. So I guess if there's no questions, let's talk about some of the yeah. Why don't we have the word of the day be unstable? Unstable. Word of the day is unstable. Unstable. You can sign in on the sign-in sheet now for the word of the day. Unstable. Kevin says it is own natural system occur in the planet climate change. I'm not sure how to parse that sentence, Kevin. I don't know if you want to jump on the mic and ask the question. The planet does have all sorts of mechanisms for climate control, right? And temperature fluctuates quite a bit over its history. The problem isn't just the temperature fluctuation. The problem is how much that fluctuation deviates from the norm. Right? We're seeing much larger changes in much shorter periods of time than anything that we know of in the whole of human history. Right, so global temperatures are about 1 degree Celsius higher than they were in 1880 when we started keeping, I'm sorry, this is 0.87 degrees Celsius greater than the average temperature since 1880 when we started keeping records. Right, so we've never seen temperatures this high, and in fact, all the temperatures we've seen recently have been historically anomalously high. Again, we've recognized this trend back in the 70s. We've known about this for a long time. If we had done something back in the 70s to stop this, then we might have been able to make this level out, but that hasn't happened. As temperatures rise, like I said, sea ice diminishes, and we're at record lows of sea ice. The polar ice caps are melting. We can see the change in polar ice caps to the point that there won't be a polar ice cap in a few years. Some countries have tried to capitalize on this. Russia, I think, planted a flag in the ocean underneath, and they want to sort of open up trade routes across the polar ice cap. which now becomes possible since there's a lot of room, since there's not enough ice. But this is a really bad thing because that ice is important for keeping our climate stable. As the polar ice caps melt, then sea levels rise. 76 millimeters. Is about 3 inches. 3 inches of sea level rise is enough to do lots of damage to coastal cities. But these trends are continuing, and they're not stopping. Right? Things are getting worse and worse. And some of this stuff gets accelerated by like the large methane leak, which puts the equivalent of 2 Los Angeleses into the atmosphere in a single year. These are unexpected changes in the global unexpected changes to the dynamics of the climate, and it has the impact of even more rapidly deteriorating our situation. Like I said, scientists have historically put the 500 parts per million carbon dioxide in the atmosphere. Carbon dioxide is only one greenhouse gas, there's other greenhouse gases, but had put the 500 parts per million carbon dioxide and the 2 degrees centigrade global temperature as the deadly cutoff points. If we cross these, then we won't be able to stop climate change from having serious effects. And we're set to blow right past these thresholds. The temperature we've already passed. The carbon dioxide we're set to pass these also. Again, so here's a graph going back 400,000 years, and the composition of CO2 in the atmosphere changes, goes up and down. It's a chaotic system. It's a complex system. But the amount of carbon dioxide in the atmosphere now is at highs that we haven't seen in the entirety of the human species. Right? There have been times in the past that the planet has seen higher concentrations of carbon dioxide, but not any time that human beings have been around, where we've moved carbon dioxide way past these historic highs, well past the averages. And this isn't going to change anytime soon. So recently there was the Paris Climate Change Conference, where they had a bunch of the big countries get together to try to come to some plans about what to do about climate change. So here's a calculator for discussing what these plans look like. Here are the different countries: China, the US, EU, and others. And here's the projections of greenhouse gas emissions, mostly carbon dioxide, over the future. Now, so this shows very clearly that if we want to stay below 2 degrees centigrade warming, well, we're already way off course for doing that. We'd have to radically change our trajectory. We'd have to basically reverse everything that we're doing right now to even get back to just the 2 degrees amount of warming. In fact, right now, if we just stay at our current levels, we're on path for 6 degrees warming by the end of the century. Again, 6 degrees warming is the temperature where we start to see massive crop failures, where the climate has become so unstable that basically all the tools that we've learned as a species for dealing with the planet sort of go out the window. And that's going to happen by 2100. This is potentially within your lifetime, definitely within the lifetime of your children. I mean, we're already seeing the effects today, but we're talking a generation or two at most before we see the full-blown impact of our last 150 years of climate change. So we're on course for 6 degrees centigrade. If we do nothing at all, 6 degrees Celsius global temperature increase. If we do nothing at all, notice the different contributions that the countries make. China makes a pretty big contribution, but in fact the largest contribution, especially as we go forward, are from other countries, countries outside of these, including the developing countries like India, Russia, Brazil. These other countries account for a huge part of this, partly because these other countries aren't part of the Paris climate change talks and they don't have plans for mitigating climate change. So if we do nothing, we're on course for 6 degrees centigrade. These are the pledges that the various countries have made by 2030. So by 2030, China has pledged to cut this much of its emissions. The US and the EU have both made very ambitious pledges to cut a huge chunk of their emissions. India, less so. Russia, very little. But these other countries have other plans to restrict climate change. If we meet all the plans that we have to date, right, this is a big if. In fact, you might even think that it's unlikely, given the other kinds of challenges that we face in regulation and so on. You might think it's very unlikely that we actually get to the point where we meet even the pledges that we have on the books today. But if we meet those pledges, we're talking about a 5-degree centigrade increase in temperature. We're talking about changing from 6 to 5 degrees, right? Let me say that one more time. If we meet all the pledges that all the government officials have made today, we're still looking at 5 degrees Celsius increase in global temperature. That shows you how completely weak these pledges are, how little effort's actually going into mitigating the effects of climate change. Right? This is the plan if we actually keep these pledges, and there's no guarantee that we're going to do that. By 2050, the pledges become more severe. China, you can see, has an even greater pledge to reduce emissions, EU and the US also. And we can see by this point, if we're all keeping to our pledges, the really big contributors to global warming are from all the other countries in India, which hasn't gotten the same kind of press that China and the US have. All of these countries have pledged by 2100 to entirely cut emissions. None of these countries have made a 2100 pledge. But again, you can see that even if all of these countries agree to cut all their emissions, we're still looking at something like a 3-degree Celsius change in climate. Right? So this isn't the kind of thing that we can stop. This is the kind of thing that's going to happen. It's already happening. It's going to happen anyway. And importantly, the way that we're planning for this is not doing very much at all to mitigate disaster. So there's some questions. Joseph asks, is our climate change laws and policies really to just try and keep temperature stable? That's a great question, and the answer to that is no. We'd like to keep a stable temperature. I mean, that's one of the goals. We'd also like to reduce greenhouse gas emissions. That's another goal. Scientists have come up with a whole laundry list of these climate goals that if we want to do something about climate change, these are the things we have to address. We have to address greenhouse gas emissions. We have to address other kinds of deforestation, these kinds of things that have a real big impact on global temperatures. The thing is that there's no direct correlation between what temperature you want and what our laws are. In fact, this is part of the problem. Let me put myself back on here so I can be passionate about this. This is part of the problem, is that we don't know how to hook up the science to our policies. In fact, the way that our political environment works is that we're often hostile to the science. There's still huge contingents of politicians who deny the basic science of climate change and have had an impact on lots of the students. So I know for a fact that lots of students in class are skeptical of climate change, disagree with climate change. And the sad truth is that this is almost entirely the result of propaganda by energy companies and other people who don't want to, who don't like the regulations that come with climate change. Energy companies don't want to stop their energy practices because they make a lot of money. So they put out lots of propaganda. Almost every bit of science that you come across that gives some reason to be doubtful of climate change, almost across the board, this is funded by the energy industry, who basically buys off scientists to publish material that's skeptical of climate change. In some cases, the energy industry even starts their own journals to publish this kind of propaganda. And it's really just false information. But the idea is to sow controversy and discontent in the people so that they don't demand their government officials do anything different. So we're in a political position right now where politicians can actually gain supporters by denying basic science and by preventing basic action on climate change. In this situation, it's really hard to have any straightforward policies about, here's what the science says, this is what our laws should be, right? Because there's this fundamental disconnect between the two. Yeah, damn you politics, that's right. This is made even more complicated because climate is such a complex phenomenon. So there is no one model of how the climate works. There is no best model of the climate. There are tons and tons of models of the climate, all of them testing different things, using different data sets, using different models, building in different assumptions about how the climate works. All of these models are useful for some purposes, useful in some situations and not others. But it's from the scientific perspective, it's kind of a big mess. That doesn't mean the science is bad. In fact, the science is really good. Our climate science, given that this is one of the most complex systems we've ever studied, our climate science is really amazing, the kinds of things we know about how the climate works. But it's very complicated, so it makes it very confusing. What the politicians would be like a simple model. Then you say, if we have this law, then that'll change the temperature this much. But if you have some simple rule like that, then it would be easy to have a law. But there is no rule like that. Instead, we have lots and lots of different models. Some of these models disagree about what will happen to the temperature, and it's the work of scientists to try to work through these models and come to some sensible understanding of the climate. But because this job is complicated, it leaves a lot of room for politicians and especially nefarious businesses who don't want to deal with climate change. It leaves a lot of room for them to sow confusion and discontent. So a lot of people don't think climate change is real. Again, it's purely the result of propaganda. Your beliefs have been bought and paid for at the expense of the planet. Climate change is it's going to kill millions of people over your lifetime, over the next couple of decades. You're going to see governments collapse. You're going to see massive unrest. You're already seeing this happen. And remember, when you were young, businesses were fighting, doing anything about this tooth and nail. So it's this disconnect between the science and the politics that leaves room for all this nefarious thing. It's also what makes it very hard to have any action on climate change. So the Paris Climate Summit was largely sponsored by large corporations, especially air travel corporations, other people who benefit a lot from lax regulations on emissions. Right? So air travel releases a huge amount of bad emissions into the atmosphere, and it's really bad because it releases it very high into the upper atmosphere, where it's a lot harder to get it out of the atmosphere. So this kind of stuff is really bad, but these are the people that are funding our governments to go to these Paris climate conferences. It suggests that these things aren't going to change very much, especially when you look at things like the VW emission scandal, where you see corporations even today still lying, still deceptive practices to try to avoid dealing with climate change. It's really disheartening. My own position is that we're not going to do anything about it. This stuff is all just going to collapse, and we're going to have to pick up the pieces. But there are other ideas of what we can do. They're not all very good, though. So I'm out of time. I need to stop right now. But look at the geoengineering lecture, and especially the Prezi. John talks about different. John's my friend. He talks about different strategies for dealing with climate change. Mitigation is about stopping climate change before it starts, and this is what scientists have been urging politicians to do for 20, 30 years. Take these actions so that climate change doesn't get bad. We haven't been doing this. Mitigation policies have failed, and that means that we've been needing to look for other solutions. One possible solution is adaptation. Adaptation basically just means dealing with it. The idea here is that, well, we can't stop it from happening, so we might as well just try to adapt. Move away from the coasts. The coasts are going underwater anyway, so you might as well just start moving now, while it's still economically feasible, instead of later when it becomes a huge environmental disaster. Right? So this isn't trying to stop climate change. This is just trying to deal with the effects. Both of these aren't very right. So mitigation has failed. Adaptation looks pretty grim. The alternative to that is geoengineering. By geoengineering, we mean building systems that actually change climate on the planet. The most commonly talked about one are aerosol injections. Aerosol injections involve putting aerosols, usually sulfur dioxide, into the upper atmosphere to hopefully block out sunlight. People like this idea partly because we have natural models of this. The kind of sulfur we want to release into the atmosphere is roughly similar to the kind of sulfur that's released in a large volcano, like Mount Pinatubo, released in 1990. So we know what actually happens when this kind of climate event happens, it does legitimately lead to a drop in global temperature, but it also leads to a huge drop in precipitation, in rain. In other words, if you start seeding the atmosphere, you get droughts. And the really bad thing about this is that the droughts aren't even, but the droughts affect certain places disproportionately. So you can see the red here is bad, and you can see that this is the temperature after Mount Pinatubo exploded. So we can see what kinds of droughts. I'm sorry, this isn't the temperature. This is the drought severity right after Mount Pinatubo exploded. So you can see the impact of droughts, the impact on water availability that this kind of sulfur release has, and it really affects the equator. Here in the equator, you see huge amounts of drought right after Pinatubo. Doesn't affect North America so much, or Europe a little bit, not Northern Europe so much. It's this unevenness of impact. The equator is going to be hit a lot more. Notice if you look at the NASA video of CO2 release, most of the CO2 is coming from North America, Europe, and China, but they're not the ones who are going to get hit hardest by the changes in climate. People that are going to get hit hardest are the poor countries close to the equator, where there are a lot of brown people that the westernized world doesn't seem to care very much about. Right? They're the ones who are going to be suffering all the impact. They're the ones who are going to have their crops failing, their governments collapsing, war and devastation. Right, so this is the challenge of climate change, right? How do you, right? So we have no global infrastructure for dealing with anything like this. Right now we have a bunch of little countries trying to solve this through cooperation. This isn't going to work. I mean, it's already failing to work. We know it's failing to work, and it doesn't seem likely that we're going to come up with nation-based solutions, especially when the impact affects nations differently, where some nations don't see the same impacts as other nations, and other nations bear the brunt of the results. We don't have any geopolitical infrastructure for dealing with this kind of political problem, right? How do we organize ourselves and coordinate our behaviors to actually deal with this? No one knows. We have the technologies to deal with climate change. We've had the technology since the 70s, but it's our failure to have the proper organizing technologies, the proper political systems, proper governing infrastructure, the proper economic infrastructure. Right? We don't have any of this infrastructure, so we're seeing our civilization collapse before our eyes. This isn't getting any better, and this is your problem. This is the problem of your generation. This will be the biggest problem your generation faces. And if your generation doesn't deal with it in any reasonable way, then you will see the collapse of global human civilization within the next 100 years. All right. Have a good day with that. If you want to come talk about chaos theory in lecture, I'm going to go to lecture now. But otherwise, sign in on the sign-in sheet, and I will see you next week. Thank you, everyone.